Good morning, dear students. In today's video, we'll discuss limitations of Bohr model. Although Bohr model played an important role in the development of structure, as it explained the stability of atom and the hydrogen spectrum, but still it has some shortcomings. So let's discuss the limitations of Bohr model. So the first shortcoming of Bohr model is it is unable to explain the spectra of atoms containing more than one electron. This point we have already discussed. I told you that Bohr model is applicable only on single electron system. Okay, like He positive, Li positive positive. Okay, so here hydrogen, helium ion and lithium ion all contain a single electron. That's why I am calling single electron system. So Bohr model is applicable only on these type of species. It does not explain the spectra of multi-electron species. Okay, so that's why this is the first shortcoming of Bohr model. Now let's see the second. It could not explain the Zeeman effect and Stark effect. So what is Zeeman effect and Stark effect? Let's see. Here I have taken an atom and suppose this is the radiation emitted by this atom. Okay, when no field is applied, then it follows this path, suppose. Okay, and when we applied magnetic field, then this radiation splits into some other lines. So this splitting of radiation in the presence of a magnetic field is known as Zeeman effect. Okay, so what is Zeeman effect? Zeeman effect is splitting of radiation in magnetic field. Now what is Stark effect? So Stark effect is nothing but splitting of radiation in electric field instead of magnetic field is known as Stark effect. Okay, so both the procedures could not be explained by the Bohr's model. That's why this is the second shortcoming. Now third, Bohr's theory does not provide any clue to explain the shapes of molecule. Okay, so this is the third shortcoming. And now fourth, Bohr's theory is not in agreement with de Broglie concept of dual character of matter and Heisenberg's uncertainty principle. So first discuss dual character of matter. Okay, so what is dual character of matter? As we know that de Broglie suggested that like photon, all the material particle like stone, ball, electron, proton, all have the dual character. Dual character means they will possess wave nature as well as particle nature. Okay, so this is the dual character of matter. So you must be thinking that if all the material particle around us have dual nature, then why they does not move like a wave around it around us? Okay, so let's see. As we know that de Broglie wavelength lambda equals to h over mb. Okay, so this is the standard formula. Now I have taken one macroscopic particle here, cricket ball, and microscopic particle like electron. Okay, so for macroscopic particle, let's calculate the lambda. So suppose a cricket ball, the velocity of cricket ball is 2500 centimeter per second and the mass of the cricket ball is 150 gram. Okay, then lambda will come 1.767 into 10 to the power minus 32 centimeter. And for electron, velocity of electron is 2.18 into 10 to the power 8 centimeter per second, and m 9.1 into 10 to the power minus 28 gram. Okay, so by using these two values we can calculate the de Broglie wavelength, which is 3.32 into 10 to the power minus 8 centimeter. So as you can see that wavelength for macroscopic particle, wavelength for cricket ball is 1.767 into 10 to the power minus 32. Minus 32 means this is a very small value. Okay, so although cricket ball is associated with associated with wavelength, but still since the value of the wavelength for cricket ball is very small, it is not in the range of measurement. Okay, so that's why the wave character for macroscopic particle like cricket ball can be ignored. Okay, that's why they not behave, they does not behave like a wave. Okay, and what about the microscopic particle? Microscopic particle, you can see that for like for electron, lambda is 3.232 into 10 to the power minus 8 centimeter, which is a significant value. Okay, so because of this large value, we cannot ignore the wave nature of microscopic particle. So that's why macroscopic particle show only particle behavior, or microscopic particle show wave nature as well as particle nature. Okay, so in this way we can say, since lambda for these microscopic particle is small, so we are considering a microscopic particle like a material particle only. Okay, like particle only, not like a wave. So as these are not wave, these are like particles only, so we can calculate the position. Okay, suppose we have position for cricket ball at a particular instant, then we can calculate its position after some time by knowing the velocity of this cricket ball. But we cannot do the same for electron, because it has the wave character too. Okay, so now, how will we calculate the velocity and position for microscopic particle? So, for this, a scientist Heisenberg gave his theory, which is known as Heisenberg's uncertainty principle. So, here we are going to discuss Heisenberg uncertainty principle. First of all, you should know that Heisenberg uncertainty principle is applicable only on microscopic particle. Okay, as for microscopic particle, they have dual nature, wave character as well as particle character. So it is not easy to determine position and velocity. So this uncertainty principle is about the same thing. Okay, so let's see. Werner Heisenberg in 1927 proposed a principle which is known as Heisenberg's uncertainty principle, and it states that it is not possible to determine simultaneously the position and momentum of a moving microscopic particle with absolute accuracy. Okay, so this statement we can write mathematically like delta x into delta p greater than or equal to h over 4 pi. Here delta x is the uncertainty in the determination of position, and delta p is the uncertainty in the determination of momentum. Okay, and as we know that h is the Planck's constant. Okay, and this sign shows that the product of these two values can be equal to h over 4 pi or greater than h over 4 pi, means the product will definitely at least equal to the h over 4 pi. Okay, now as we know that delta p momentum is equals to mv, so delta p will be equal to m delta v, because m is constant here, because we are calculating for same microscopic particle, so m will be constant, but velocity will change. That's why m delta v I have written. So we can put the value of delta p in this formula, and then we'll get delta x into m delta v greater than or equal to h over 4 pi, or delta x into delta v greater than or equal to h over 4 pi m. Okay, one more thing, suppose we are doing a calculation, 4 into 5 equals to 20. Okay, now I want to put a number instead of 4 which is less than 4, so I have put 2 here. Okay, so since the product of these two numbers are 20, which is constant. Okay, so and I am decreasing the number, I am decreasing the first number, so I have to increase the second number because the product is constant here. Okay, and suppose I am increasing the first number, as I'm writing 5 on the place of 4, then I have to decrease this number. Okay, so similarly in this formula, delta x into delta p greater than or smaller than greater than or equal to h over 4 pi if delta x, which is uncertainty in the determination of position, is less means we are measuring the position more accurately. Okay, then delta p will be large. Okay, then the uncertainty in the momentum will be large. And oppositely, if delta p is smaller, means we are measuring the momentum more accurately, then delta x will be less. Delta x will be large, means the uncertainty in position will be more. So this is the relation between delta x and delta p because of the constancy of product. Now